Hi, welcome to lesson 5.4, slope as rate of change in chapter 5, modeling with graphs. So last day we learned about slope and you had graphs and you could count rise and run and calculate the slope as rise over run, or you could be given two points, their coordinates, and you could calculate y2 minus y1 over x2 minus x1 and come up with the slope of the line. Slope is equal to the change in the y's over the change in the x's, change in dependent variable over change in the independent variable, change in the vertical values over change in the horizontal values. All of those mean the same thing. So we have a graph here, and it shows a relationship between the height of a parachutist in meters and the time of descent in seconds. So the first question says, find the average rate of change in height relative to the change in time. Well, if you're looking for a rate, an average rate, that's going to be division. Kilometers per hour, meters per second, how many donuts I can eat per hour, that's all rates. Okay, there has to be something happened per some sort of time frame or other relative frame. Okay, so the change is in change in height relative to the change in time. So we know we want change in height over change in time. That's going to give us our rate. So if we look over here and we're like, okay, at time 0, the height of the parachutist is 500 meters. I can go along and find another one. Actually, that's not bad, 20 and 400. But it's really easy to just go to this one, which is at time 100 seconds. The parachutist is at a height of 0. I'm going to use these two endpoints to calculate the rate of change of the parachutist. So I know that the parachutist started at 500 meters high and landed on the ground and was at a height of 0 after 100 seconds. So I don't even really have to subtract using that one. It's pretty easy to see that this guy went down 500 meters in 100 seconds. And so that's 5 minus 5 meters per second. And if we remember back to the last lesson on slope, the line is falling as you move from left to right, and so it makes sense that it's negative. It also makes sense that the height is getting less and less as he approaches the ground. So negative rate of change. Okay, next part is B. Explain the meaning of the average rate of change. Well, in this case, this rate of change is meters per second. This is the rate that he's traveling. We call that speed. So it's the speed that the parachutist is approaching the earth. C. State and explain the meaning of the vertical intercept, and then we're going to do the same for the horizontal intercept. So this is the vertical axis. It's the dependent variable. It's our y-axis often, but in this case it's an h-axis because it's height. The intercept is where the line crosses the y-axis or the vertical axis, and that point has coordinates 0, 500. And what that means is when we're looking for the vertical intercept, we're saying, okay, well, when the horizontal value is 0, what is the value of the vertical? What's the vertical value? So in this case, time 0, we're at a height of 500. Well, what this means is that that's the initial start. This is the start height. Start height of the person. So it's probably the height of the plane. It's the height at which he jumps out, because we're going to start timing after the person jumps out of the plane. So it must be starting at a height of 500 meters and then falling, falling, falling. And then this one is the horizontal intercept because it's the point on which the graph crosses the horizontal axes. And at that one, it's got coordinates 100 and 0. And you can see that, oh, what's happening there? Well, at 100 seconds, the guy hits the ground. Okay, that's at 100 seconds is how long it takes to land on the ground. He's landing on the ground because his height is 0. Okay, next example. In 1971, there were 323,000 full-time university students in Canada. In 1997, there were 544,000. Find the average rate of change to the nearest 100 students per year. Well, again, it says find the average rate of change. So you know you're doing division because a rate is always something per something. And it says to the nearest 100 students per year. So it's students per year. So we know students is on the top of this fraction. Students per is the division and year is going to be on the bottom. That's the rate that we want. So we need to figure out a rate, we need a change in the number of students over the change in the number of years. Well, from 1971 to 1997, that's 26 years. So we can say, well, I can see there's 26 years between those two. And if you find the difference in the number of students, you're going to find that that is 221,000 students. And when you divide, you're going to get 8,500 students per year. Now, if we relate that back to what we learned last day, you can kind of make these coordinate points. You can say in 1971, I have 323,000 students. And in 1997, we have 544,000 students. To find the rate, or the slope of that line, we would have to have the change in students over the change in years. And we kind of intuitively already did it that way, but I'm just showing you how you can relate information like this to the slope formula that you've used before. So we're going to find the difference in our y's and a difference in our x's, which is the same numbers we already came up with before. Students per year. Okay, so the average rate of change is basically the same thing as slope. Slope is rate of change. Number 3. Okay, this one's really old. When the internet was first introduced to the public, plans required payment based on the number of hours spent online. Shannon's internet provider charged a flat fee for the first 10 hours of internet access per month, plus an hourly rate for additional access. One month, Shannon was online for 15 hours and paid $18.75. The next month, she was online for 27 hours and paid $39.75. What was the hourly rate for hours above 10 hours per month? So we want the hourly rate. So the hourly rate, we're looking for a rate. We want to know how much money you have to pay per hour. That's what the hourly rate is that we're looking for. So we know we want to find the difference in dollars over the difference in hours. This one has an interesting spin on it because it says, you know, for the first 10 hours, it's kind of a flat fee and then it goes up after that. So if you can just kind of imagine over here to the side a graph of this, we know that for the first 5, 10, 15, 20, 25, okay? 5, 10, 20, etc. Okay, so if this is my hours on this axis, and then my vertical axis is going to be my dollars, we know that for the first 10 hours, it's a flat fee. There's no change. Whatever the price is what you pay for the first 10 hours. After that, however, it goes up. And we know the first price that we pay is $18.75 for 15 hours. Whoopsie. And then we know the next one is $39.75. And that happens when it's, how many hours? 27 hours. So something over here. Okay, and it keeps going, it goes up on an angle like that. Okay, so we know a visual of what's happening. The first 10 hours is some price that we don't know. We need to find the rate, what we're paying per hour once we're above the 10 hours. So we don't really care what we're paying for the flat fee. We want to know what this rate is. What's the rate of increase of this line? So that's just the slope of this line. So all we need to find the slope are 2 points. And we have 1 and we have 2 points. So the rate is going to be the difference in the prices that she paid. So $39.75 subtract $18.75 over the difference in the hours that she had service for. 27 hours subtract 15 hours. And when you do that, you get $21 over 12 hours. So you get 7 over 4 is the slope of the line, and it's also the rate. $7 per 4 hours. Well, that's kind of an odd way to write that. Instead, I could go 7 divided by 4 and think of that as a decimal as 1.75. It makes sense in this case to say it's $1.75 per hour. We don't really want to say a rate of $7 per 4 hours. That's not the way you need it. You need to make that to be a 1 hour. So dividing 7 by 4 and just writing it as a decimal gives you that. 175 per hour. And that's what makes sense to say. Okay, so now you've seen, oh, I should just make a note of this. This graph over here, this is called Piecewise Linear. There are 2 lines on this graph, this one that we were interested in and the other one. If you were to come up with an equation for this graph, which we're going to be doing in the next unit, you would need to have 2. You'd need to have one for this portion of the graph, and you'd need one for this portion of the graph, because lines are straight with rulers in math, and so these are 2 different lines because you have a bend in it. Boom, boom. So 2 separate lines. So we found the slope of this line. We also know, because lines have the same slope all along, right? They don't change. So the slope of this line is consistently at 1.75, whereas the slope of this line, we know that's a horizontal line. There's no rise, but there's a run. And so the slope of this part is 0. So they have to be 2 different lines if they have 2 different slopes. Okay, that's it for this lesson on 5.4, and go do some practice on this. Okay, so slope is the same as rate of change.